So hi everybody, my name is Mostafa Mokhtar. I work for Cloudera and I primarily work on Impala performance. So the talk today is, there's no benchmarking, there's no us versus them. It's mostly going to be around Impala's architecture and how we make certain things in Impala work fast. So it's a bit of a technical deep dive into things, not too much. I'll try to keep it relevant. Thankfully, there was the talk before this one was a good segue, moving from machine learning to analytics, databases, and whatnot. So agenda today, we're going to go over the history and motivation why Impala exists, go over Impala's architecture, and then we'll cover two different aspects of Impala's performance. What optimizations we do on the front end in terms of query planning, what we do with statistics and whatnot, and what kind of optimizations we do in the back end in order to make query execution faster, more reliable, use less CPU, etc., etc. So the big data revolution, I mean, some people say it started with Hadoop. Other database old-timers say big data has always been there. I think they're both correct. But what happened with Hadoop is that users were able to store tremendous amount of data, but then this data was just sitting. And back in the days, a lot of analysts knew SQL, and they said, hey, we want to use SQL and Hadoop. And Hive came. The problem with Hive, I mean, Hive was great. It allowed you to run some kind of analytics on data stored in the AGFS. It supported different file formats like Parquet and ORC, which are columnar. Also supported the text, Avro, and RC. It ran at scale. It was fault tolerant, but it was very, very, very slow. And that was a bit of a problem. So at any time, if anybody wants to ask a question, feel free to stop me and ask me. And then after people started understanding, hey, we have a lot of data that we want to analyze, Hive is very slow, and then there came the opportunity for Impala. So Impala is written in C++, not Java. Many of the problems that plagued Hive and continues to plague many of the current SQL Hadoop systems is that they're written in Java. Java is easy to develop against, but then you end up hitting issues like GC and weird pauses, and you're not able to optimize the system to leverage all of the microarchitecture features that exist in today's systems. Also, Impala is meant to be scalable. It's meant to run on hundreds of nodes. It supports different file formats and also different storage systems. So it could run on HDFS, on Amazon S3, on Microsoft ADLS, Apache Kudu, and HBase, and whatnot. Also supports Kerberos, SSL, authentication, lineage, and all those kind of cool features. Some kind of overview of history. First commit was May 2011. First release was a year later. And one of the things I'm most happy about is last month we graduated to a top-level Apache project. So everything we do is open source. All of our bugs, some of them can be embarrassing, are there. All of our changes, which also some of them can be embarrassing or great, are there for anybody to go and review and ideally contribute. So also, as other folks mentioned, the SQL and big data race is on. There was Hive and Map produced, then came out Hive and Tez. It was slow but faster. And Hive and LLP, which is a little bit faster. And then there's Spark SQL, there's Apache Hawk, which is basically Postgres with some glue. Sometimes they call it Greenplum or Hawk. Amazon Redshift, which came out of some acquisitions, and Apache Drill, and Presto, which many folks are familiar with. So having that said, I'm going to switch to giving an overview of Impala's architecture. So the blocks in green are what Impala is. So Impala, it's a query engine. Impala itself doesn't store any information. Impala relies on a file system like HDFS or a storage engine like Kudu or HBase to store the actual data. Impala, you could insert data through Impala. You could retrieve data through Impala, but Impala itself doesn't store any data. There are some, also Impala integrates with some other services like Sentry for authentication privileges, the Hive Metastore, and the HDFS name node, where basically, I'll go over these now. And of these services, there's the state store, which is a simple pub/sub service that distributes metadata and cluster membership over the cluster. There's the catalog, which basically interacts with third-party metadata providers, as I mentioned, like HMS, Namenode, and Sentry. And then there's the Impala daemons. And these are the actual nodes that do the actual work that run the queries. And one of the cool or interesting things about Impala is that you can connect to any Impala daemon and run a query. It's not like you have a single master that you can connect to. This gives you the flexibility. If you use Impala daemon, and it goes down, you could connect to another one and move on. Then next, as I mentioned, this is like the top section is the metadata. So in Hive Metastore, you store basically the logical mapping of a table to a path into HDFS. So you say I have my database DB1, I'm storing in a table foo, and it has a certain path in HDFS. And this is how Impala is able to find if it wants to scan this particular table, where in HDFS it needs to go. HDFS, basically it's a distributed file system. Sentry is used to store roles, privileges, and limit access to users, etc., etc. And for the Impala, it's split in both. There's a Java front end, which is responsible for query compilation and metadata. It also interacts with the catalog. There's the query coordinator, which is responsible for running the query, and there's for coordinating the query. And there's the executor, which is the component of Impala that executes the actual query. And as you see here, the backends are written C++ for efficiency and performance reasons. Next, I'm gonna basically show you what happens when you go and create a table through Impala. A user connects via JDBC or ODBC to one of the Impala daemons and says, go create table foo. The Impala daemon goes to the catalog and say, hey, please create this table on my behalf. The catalog goes to the HMS, creates the table, and then say, hey, the HMS would say, yes, table was created successfully. The catalog talks back to Impala daemon, say, we're good to go. And then this is where the state store comes in. One of the challenges with MPP is that you need to make sure all of the nodes in the system are in sync in terms of like what metadata is there, what cluster membership is there. So in this case, a new table was created. The catalog told the state store there's a new table, and the state store would basically propagate this information across the cluster to make sure all of the Impala daemons are in sync together. Next, I'm going to cover a select query. Same thing happens via ODBC or JDBC. You connect to an Impala daemon. You say, hey, the query gets compiled, and then the coordinator will take this query, create what is called a plan fragment, and then it will ship the plan fragments for each one of the Impala daemons, say, go and execute these set of operators. These operators will go and then read the data from the storage system based on the query. And then you could end up with a case where you have to redistribute the data in terms of shuffle, broadcast, do joins, etc. And then eventually return the results back to the client. So I think by here we're done with the architecture overview. If anybody has questions, I'll move on. Cool. So as I mentioned earlier, one of the key features for Impala is performance. Impala was designed with performance as a primary goal. And so making sure that release to release Impala's performance improves is something very fundamental to our core. And as you see, like over the past 2 years, we improved like TPCDS performance by almost like 10x and TPCH by 3x. Of course, if you run a workload, your performance will vary because of these are like different workloads, have different query plan shapes, etc., etc. But in general, we've always been focusing on making things better, faster, and more efficient. Now I'm going to talk about Impala's internals a little bit. First phase, I'm going to be talking on about query planning. So Impala has a two-phase cost-based optimizer. First, it generates a single node plan where it goes and does all of the different transformation rules, join ordering, partition pruning, etc. And then after it created the single node plan, it will then convert it into a parallel plan. It will go and add exchange operators, which are responsible for redistributing the data across the nodes if needed. And then it will pick different join strategies, like do a broadcast here, a partition or a shuffle join there, etc., etc. And then query execution is broken into fragments. Each one of these colors is a fragment. A fragment is basically a set of operators that execute on one or more nodes. Moving on, metadata. One of the challenges basically with running on a Hadoop is that sometimes big data problem translate to a metadata problem in the sense that you could have a table with hundreds of thousands of partitions and millions of files, right? The act of going to talk to HMS and the HDFS name node to ask for all of this information itself can take very, very long time. And as I mentioned, Impala was built from the get-go in order to run queries fairly fast. So it tries to cache some of this information whenever possible, and we have other mechanisms to deal with stale cache to basically refresh the metadata and whatnot. One of the challenges we dealt with this caching is that when you have a lot of data to cache, and as I mentioned, the catalog and the front end are Java, they can be problematic. So over the past year or so, we ended up moving all of our internal caches to use flat buffers. So this makes the storage significantly more efficient. Other tricks we try to play is that we try to create thread pools to make this metadata loading faster, because in many of these cases, it's latency driven. With kind of keeping metadata in mind, one of the other cool things in Impala we do is we store statistics in an HLL. I think someone in the previous presentation was mentioning that, which is basically stands for hyperlog log. And this makes computation and keeping track of the number of distinct values for a particular column significantly faster and more efficient than many of the other systems. Interestingly, the number of distinct values plays a very big role in terms of like query optimization, ordering, cardinality estimation, etc. And it's significantly more efficient to use an HLL because basically it has a fixed memory footprint. The HLLs we use are sized at 1 kilobyte per column. And this is significantly more efficient than saying select count distinct for all of my columns in the table. And in many cases, it becomes prohibitively expensive. The other cool thing with HLLs, we're able to do incremental stats. Like you add more data, you compute stats in the last data set, and you merge the HLLs, and you get a fairly accurate number. Now I'm going to jump a little bit into query optimizations. In many cases, when we talk to our customers or our users, we tell them it's very important that you go and actually compute statistics for a table. And in many cases, they say, oh, I only have a 2-table join. How bad can it be? So for these set of slides, I'm going to walk you through basically this query over there. It's not too complicated. Joining table named orders, other one named line item with a bunch of filters. And I'm going to show you like all the different optimizations, not all, like some of the different optimizations that Impala will do. So if you look at the actual query text, it's basically saying L comment like some string, L receipt date greater than something, L part key less than something, right? One of the difficulties as people, as they're writing queries, always think whether the query writing is optimal or not. And basically, if you look at these predicates, there's a predicate, there's basically almost a regex expression against a string column. There's another inequality expression, another string column, and there's another equality expression against what looks like an int or a long, right? So what Impala does, it uses the statistics that is stored and captured to basically reorder these predicates and run them as efficiently as possible. So it will take into account the cost of the filter and the selectivity. So in this case, if you could see here, the first predicate is L comment, but the first predicate gets applied is L part key. And that is because this is the most predicate to apply first. Other things we try to do is basically we mitigate. Sometimes you could have correlated predicates. For instance, if you're saying, give me all sales for cars that are Toyota and model is Camry. These two are correlated, but the basically query optimizer can't really tell. So using the statistics, we're able to kind of play some tricks to basically mitigate this kind of dependency and come up with meaningful estimates. Other things we do in general that are kind of difficult in big data. So if you're using, let's say, MySQL, Postgres, or any of the other systems, you could go and declare these primary key and foreign key constraints that the query optimizer is able to use to come up with better cardinality estimation. But in the big data world, this information doesn't exist, and people don't like to do that. So what we try to do in Impala is we look at the number of distinct values, and we look at the row count, and we try to pattern match these relationships to basically figure out whether this is a primary key to a foreign key relationship or this is a many-to-many relationship. And basically, we take this into account in terms of like ordering the joins to get the most efficient plan possible. Other than that, we compute the selectivity of the scans. We determine which table is on the build side versus prop side. In this case, also, we've tried to figure out whether we do a broadcast or a partition join. And identify which columns benefit from runtime filters. I'll talk about runtime filters in more detail. But basically, all of these things as they add up, they will create basically a big delta between running with or without stats. So we always encourage our users to run with statistics. I'm sure in the future, we'll eventually get to the point where we automatically compute stats, but we're not there yet. Now, moving on from the front-end discussion to the back-end. So Impala's query execution is not based on MapReduce. Operators within Impala, as for joins, sorts, and AGs, they're single-threaded, which, yes, it's a surprise, but they're not multi-threaded, but they're very, very efficient. I'll go over some of the tricks we do to make them very efficient. Execution is row-based, but it's not row at a time. We use a batch at a time. Batch within Impala is 1,024 rows, and it has a Volcano-style execution, if some of you guys are familiar with that. Scans are multi-threaded. We have scanner threads, which are responsible for applying filters, projections, and whatnot, but also we have I/O threads, which are doing the I/O. This segregation gives us allows the ability to play really cool tricks and basically keep the system busy as possible. I mentioned before we support different file formats, and we support nested data that's only for Parquet. And I'll also talk a little bit more about code generation in Impala. And also, as I mentioned, Impala is only used for query, almost basically execution, querying, and inserting data. It doesn't store any indexes itself. But we support partitioning like many of the other systems. It's not like a B+ tree or anything, but basically partitioning allows the user to physically divide the data. So when they run the queries, they could only query the data they need. The common term used is partition pruning, which basically gives you the ability to only filter partitions. This can happen in two different ways. In this case, create table sales, partition on year and month. If you have predicates on year and month, you do the filtering. The other example, you create table sales, but your partition on date key, which is a surrogate key. If you're joining on that date key, we're able to filter, prune the partitions dynamically at runtime without having the user to do any tricks there, or to do anything there. Next, I'll be moving to some optimizations we added in Impala. It's not exactly in Impala, but basically us working closely with the Parquet community to add more features in Parquet in order to make Parquet scans faster. So one of the cool things about Parquet is that it stores more than just the data. It stores some metadata within the files. And basically what it stores is that per column, it stores min and max values per file. And what we're able to do in Impala is basically take a predicate, evaluate these predicates against these statistics, and decide whether we need to read the file or just like skip it completely. So what we added in Impala is that you could create a table and add a sort by clause. And the sort by clause, this would be a set of columns that are commonly used in highly selective filters. And any inserts that go through Impala would basically add a sort by operator to the query to basically write a file in a way that's efficient as possible. I mean, of course, the benefits you get is that you get better compression when you sort the data, and also your min-max filters and your min-max filter becomes significantly more selective. Also, we're working with the Parquet community to add more indexing support within the Parquet file to allow you to skip rows within the file a bit more efficiently. Next, I'll go over some examples, whether this is fairly common. And basically, these are patterns or anti-patterns that we've seen users of Impala or other Hadoop systems follow when they basically need to optimize the read throughput for their queries. So in this particular case, we're interested in querying by hour or day. But basically, if you go and partition your data by hour or day, you're going to have hundreds of thousands of partitions, and basically metadata is going to explode, and it's going to be pretty bad. So the solution is basically partition by year, month, or just month, and then you could sort by day and hour. In this particular case, as you see, the query has a filter on year, month, day, and hour. The net benefits or gains you get here are just like as an example we had using the data set we have, but it gives you an idea that you could make tremendous speed up improvements within Hadoop, which are not very common for highly selective queries. So now basically you could say, I'm interested in kind of needle in a haystack kind of query. You could run these within a couple of seconds or even less if you partition your data, partition and sort your data the right way. Another way of doing things, if you're always interested in basically the last interactions for a given customer in the last day or year, right? In this case, what you do is that you partition by year and then you sort by customer ID. And this gives you like huge speed up here as well. Moving next, I'll talk about code generation within Impala. So basically, Impala uses runtime code generation to run query-specific code in the inner loops, and the goal is to avoid virtual function calls and lots of branches, if else, and offsets. The problem is that when you write a database, you write it to handle different data types: int, long, decimal, string, boolean, double, etc., etc. And in many cases, you need to read a row and apply filter. If every time for every row you go and check, is this filter an int or it's a long, and you need to go and make the correct virtual function call, the code becomes very, very, very expensive. And I'll go walk through a detailed example there. So the idea behind code generation is basically to move all of these branches and make your code as efficient as possible. This kind of list of like what kind of operations are supported have code gen support in Impala. Almost most things are supported. One of the other things we try to do is code generation is not always free. So basically to look at the information that's available at compile time and then create some code that's optimized to do that and then run it. Sometimes it's very expensive. For instance, if you have a very, very long expression that basically does like a group by in 1,000 columns or something, code generation can be expensive there. So we try to minimize that kind of cost. Also, what we try to do is using statistics, we look at the query that is about to run and see if this query is long enough if the query is long enough, and then we decide is it worth code generation or not. So if you have a query that reads 100 rows or 1,000 rows, there's no point code generation because it'll be very, very fast anyways. Next, I'm going to walk through a detailed example. So in this case, I want to do a simple order by. And in this case, I'm just ordering by order key. So in many cases, the bottleneck in terms of sorting or ordering is going to be a method that basically compares two different rows. So in this case, you have the left-hand side, you have the right-hand side, and you could also be ordering by multiple columns. So in this case, I'm just ordering by order key, which is a single column, but you could be ordering by order key, extend price, etc., etc. So your code has to be generic to handle any arbitrary case, and the problem with writing generic code ends up being very, very, very slow. So here, I'll walk through the code first and then go to more details. You take the left-hand side value, right-hand side value, and if one of those is null, you have to figure out if you have nulls first or last. So basically, in many cases, when you're writing an order by operation, you want to know if nulls are first or last, because your application might depend on this information. And then you compare the left-hand side and right-hand side, and then return which one is bigger. Here's the problem. Get value would have a switch statement saying, if I'm an int, do this. If I'm an Boolean, do this, etc. Same thing for the right-hand side. These are unnecessary branches, which you actually pretty much know at compile time. And then here you have the comparison. It does kind of the same thing. It has a virtual function call and a case statement. All of this is like ridiculously inefficient, right? And this is what the pseudocode for the Codegen code looks like. And these are like all of the different optimizations. So in this case, I was comparing on one column. I had this loop. This loop has a condition where you have to check for every row. So basically, we know that there's only one column. So basically, we remove this loop. Virtual function calls got removed, and a loop got unrolled, and all this becomes very, very very efficient. To give you an idea, this code would burn 90 cycles per row. This guy will burn 9, so that's a 10x speed up, right? And this kind of optimization we do for basically all of the performance critical areas where evaluating a filter, joins, aggregation, sorting, evaluating complex expression, anything that's performance sensitive, we try to code generate to get this kind of efficiency. Kind of switching gears a little bit, next couple of slides I'll be talking about aggregation. So in general, in a distributed system, when you're doing a group by operation, it's usually split into 2 or more parts. First part, you do a pre-aggregation, and then you distribute or hash distribute the data over the network based on the hash keys, and then you do the merge, which is the final aggregation. This works really well for a query like this, like give me all sales by customer ID. The cardinality for customer ID, which is number of distinct values, is going to be high, but it's not going to be insanely high. So you're going to be able to get meaningful reduction from the local aggregation here. But this ends up being problematic if you have a query that looks like this, select distinct star from a very big table. In this case, you're going to do a pre-aggregation. You're going to burn a ton of CPU, and then possibly use a lot of memory, redistribute the data, and pretty much do the exact same work here as well, right? And as I mentioned, the problem with doing that kind of stuff in Hadoop is that it's very hard to have a primary key or have fairly accurate stats. So the goal for us is basically do something that dynamically adjusts to the incoming data. So what we did is basically we added an algorithm that dynamically estimates the reduction of data. And we now, instead of having an actual partial aggregate, we have a streaming aggregate that will never spill. So this aggregate will never spill. It will try to reduce the data size. If it realizes it needs more memory to reduce the data size and data reduction is not worth it, then it's actually act like a pass-through operator. It's not going to try to build a huge hash table, which is going to be wasteful. And in this kind of cases, we've got like 40 to 50% speed up in terms of like memory and CPU for high cardinality aggregations. And I mean, the best thing of this, like the user doesn't have to do anything. Streaming aggregations are enabled by default, and they work pretty well in general. Next, I'll switch to optimizations for selective joins. So the name for the optimization we have Impala is called runtime filters, and basically the goal is to optimize equi-joins, whether you're joining with a partition or an unpartitioned table. The idea is to avoid processing rows, doing I/O, basically avoid processing rows and doing I/O, and avoid sending these rows to the join. The goal is to filter as many rows in the scans as much as possible. The problem is that you could have a query, and there are no indexes that could basically help you figure out, if I have a filter on table A, what kind of filter would that translate on table B? It's hard to have these kind of indexes. And basically, the goal behind runtime filters is to do that dynamically during query runtime. And to achieve that, we use Bloom filters, which are a probabilistic data structure that allows us to query, store, and query keys. To give you a demonstration, kind of started like a basic business questions. Find the customers that match a certain demographic and give me the amount of sales they've made or purchases they've made. And this is the join graph. You have sales, you have your customers, and you have customer demographic. And sales doesn't join with customer demographic, it only joins with customer, and basically this is the relation. And this is your query, like give me the email address of users that have made those sales, that are male, that have a lot of money, and credit rating is low, right? The problem is you have a fact table which has like 43 billion rows, customer table which has pretty much 4 million rows. This join is huge, this join is also going to be huge. So the idea is like, how can we make this more efficient? So in this case, we use the Bloom filters. So what we do is we read the customer demographic, SK, which is the key that joins between customer and customer demographic and customer, and we build the Bloom filter, and we push the Bloom filter to the scan of customer. So customer we expected 3.8 million rows. We reduced that to 4.6 thousand rows. So that's like almost like 800 times reduction. And then we do the same thing again. As we're scanning customer, and after we filter it, we create another Bloom filter, and then we push it to the scan of the big fact table. So that fact table is going to scan 43 billion rows, and that's reduced to 49 million. That's 3 orders of magnitude reduction. So basically, all of this have kind of made the query significantly more efficient and run much, much faster. This kind of optimization works in both ways. You could run it, you could use it to skip partitions. So if the join is in a partition column, you'll be able to avoid reading these partitions and stop doing the I/O. And if not, then you will do the filtering on the row level. In the next release, what we're working on is we're extending the runtime filters to keep track of min and max values. And we take these min and max values and push them to the scan. In cases if you have good min and max stats for Parquet, this is going to be very, very efficient. And this will be like your ideal case scenario. And this whole kind of technology is very, very useful, especially for like drill down queries where you have like a big fact table that joins with multiple dimension tables. So all this wouldn't be efficient if the runtime filter implementation itself is not efficient. The problem with the Bloom filter is that you have to query it multiple times. Think of it as a fairly small hash set. So usually Bloom filters, they have multiple hash functions. So what we do is when we store a key, we make sure that this key maps to a single cache line. So misses, again, you get only one cache line miss, but then the multiple hashing for the Bloom filters, they all end up hitting the same cache line. So when we do that, we're able to make this like fairly efficient. Other thing we do is we use AVX2 instruction sets whenever they're available. If not, we use SSE. If not, we use something else. One of the other key things for Bloom filters to be useful is basically when you store information and want to query it, Bloom filters have a false positive rate. The false positive rate has a ratio between, I mean, it's dependent on number of keys in the Bloom filter and the Bloom filter size. So it's very important to match the Bloom filter size with the expected number of distinct values. And this is what the planner does. The planner looks at the cardinality estimation and then decide what kind of Bloom filter, what Bloom filter size we should use. There's also cases when we get it wrong. And if in cases when we create a Bloom filter that's all set, basically all of the values are set, which means it's not going to give us any selectivity, we actually disable it. The other thing, if I have a scan that's basically evaluating as a Bloom filter and nothing is getting filtered, we'll also disable it. And I mentioned these. Also, Bloom filters do use code generation. So basically, in cases where you have multiple Bloom filters and you have a loop for each Bloom filter do this, we code gen this whole thing and then unroll the loop. Questions? Cool. Yeah, so next I'll be switching into something a little bit more low level than that. So a while ago we did some kind of overview of TPCH running concurrently and want to understand at the lower level what is happening. Are we efficient as possible, or are we leaving some performance on the table? So kind of did this whole study and then realized, I mean, all this is in terms of CPU cycles. We realized that the probing for joins is very expensive. That's the big yellow circles. It's like at 48%. So we started like to zero down on it. And using some fancy tools, we started analyzing the cycles spent overall when running the workload. Total cycles is the 100%. We realized that 75% of the cycles is cycles no execute. Cycles no execute means that the CPU was waiting in general. This counter basically says that 72% was waiting on data from L1 cache. And basically this says data from L2 cache, and this is TLB misses. So when you look at this, basically this means that 75% of the cycles were actually the CPU was waiting. And when the CPU is waiting, it's not idle waiting. It's actually busy waiting, right? And this is not because of spillock or anything, but basically if you're dealing with cache misses, you're busy waiting, as in the CPU is going to be actually spinning. You realize, OK, this is pretty bad. We need to go and improve that. So we went and looked at our join code. And the join code kind of looks like this. So earlier I mentioned that Impala's operators, they operate at a batch. So basically I have a batch of 1024 rows. So for I equals 0 to 1024, grabbing the probe value. And then you take the probe value, you hash it, and figure out what partition. So our hash table is partitioned, so figure out what partition ID, and then do a probe into the hash table that you've built. And the problem is you have all these data dependencies that this guy depends on this guy depends on this, and then you go and probe the hash table and you end up with a cache miss, right? And because of these data dependencies, it's very difficult for the CPU to go and prefetch that information. I mean, even if it's like a hash function. So it's very difficult to predict what the hash function is going to generate. This ends up being like really, really inefficient. And we looked at this to our, surprise, looking at just this kernel as a whole. These are cycles where we're not waiting, and like these are cycles when we're waiting. So basically, 2/3 of your cycles are wasted due to cache misses and bad pipelining. So then we looked at this code, like, OK, how can we rewrite it and get more performance out of it? So first thing we did, well, let's put a prefetch instruction. And so actually we did two things here. So we added a prefetch instruction, but we also broke these two loops. So for basically 0 to 1024, get the value, hash it, etc., and then prefetch it. So basically in this loop we have some data dependencies, but basically the compiler would go and unroll this to some extent, and we actually do the prefetching there. And the cool thing is that since I have 1024 rows, by the time I've prefetched the row and then I try to probe it, very likely it's going to be in your low-level cache. Our early attempts was prefetch, probe, which didn't give enough time for basically the memory controller and all that to fetch data from memory to the low-level cache. So having this kind of breaking up this loop into breaking the loop into like two parts and doing the prefetching here and probing there made things significantly more efficient. And then of course here we're getting like a lot of cache hits. So this is kind of like the progression. We started here by adding the pipeline. We got so much better, but we still had a lot of cache misses. And then we added pipeline plus prefetching, and then we got like tremendous speed up in this kernel by itself. So kind of lesson learned from this like past thing, don't underestimate cache misses and try to measure. Usually it's a little difficult to say I'm burning so much CPU because of cache miss. Usually if you go look at the low level, you'd find something like a jump instruction burning like so many cycles, which doesn't make sense. Usually that's like a description that you have like a fairly severe cache miss. And with the scheme that we kind of learned over the past couple of years, we were able to speed up joins and aggregations by 30 or 40% if they don't fit in low-level cache. And the best part is that things didn't regress. If you had like a very small 1 megabyte or 2 megabyte hash table, things didn't regress.
Can you go back to that last slide?
Sure.
So the ratio of misses is still 1:1. Are you guys still working to optimize it?
So the number of misses has gone down significantly.
Correct, but it is still 1:1. So the question is, are you guys still trying to optimize it, or are you guys?
So what we did is that we realized where these stalls are not exactly cache misses. These end up being TLB misses. And so what we need to do is that we need to make this whole thing TLB friendly. The problem is if you have this much to improve, and we became here, then this is great. But now if you go and fix the TLB misses, you go from here to like maybe there. So eventually you end up having like diminishing return in value, and then we basically have bigger problems to solve. Spending a couple of weeks and making joins 30-40% faster, that's great. If you spend another like month and make it only 10% faster, then like And that's pretty much it. This is the last slide I have. So in Impala in general, we continue to focus on performance and scalability. Parquet optimization is still like an area of interest. Although we made some improvements with the sorting of tables and whatnot, but still we could make it so much better. Metadata, we're constantly making our metadata story better. The problem with metadata becomes a big data problem itself. Lots of customers have like tens of millions of files. Trying to cache those and making sure everything is coherent ends up being problematic. We're working on improving an RPC layer. So now we're working with customers who want to run Impala on a couple hundred nodes, like 400 nodes and bigger. We had to rethink some of our infrastructure. Reliability, kind of graceful node decommissioning, if you're doing hardware upgrades and whatnot, better resource management, and we're constantly making things better run in the cloud. These continue to be some areas in focus, and that's it. That's what I had. No singing? Thank you. Questions? Go ahead.
You were saying we should absolutely run Impala with statistics.
Yes.
What does that mean exactly? Is that just a flag that we need to set? Or?
Compute stats.
Okay.
So basically, when you add a new table, you start querying it, you'll see in the explain plan saying statistics missing for so-and-so. All you have to do is say compute stats, and then you're good to go. We're also working on adding sampling stats. We have a fairly cool implementation for sampling stats where we take multiple samples using HLL, and basically we see how the number of distinct values grows, and then we try to fit a curve and try to find the best equation that fits the curve, and basically end up projecting this will be your NDV. It's something pretty cool we're working on that should be out in the next couple of months. Yes.
The query plan, is it impacted by if your node usage is skewed in terms of data distribution?
No. What Impala does is it tries to optimize for locality. So it will try to find where the blocks are. So basically it will say, I need to query a particular table. It will go to the HDFS, find where the location of all the blocks, and then try to schedule the scans and the query execution where these blocks actually live. So one of the things I mentioned, it's in the slide, but I forgot to mention out loud, is that Impala uses short circuit reads, which basically means if Impala read the file once and now it's reading it again, and the file happens to be the file system cache, you end up basically reading the file from memory, and it's able to make things pretty fast if you're IO bound in that sense. Good.
So right now when you run Impala, you have the statics pool for Impala, right? If
Right.
you run it with Yarn, for example.
Yes.
Do you see a future where you'll have dynamic pools for Impala so that it can run alongside Spark jobs? Or
So we tried doing that with something called Llama, but then it didn't work quite well. The problem is Yarn is fairly slow in terms of reallocation and deallocation. And the idea about Impala is that we want to run queries within a couple of milliseconds. So we had to give up something in order to make it work. One alternative to use static partitioning or run Impala on a subset of nodes. This is an alternative. Cool. Thank you.